Hi, welcome back. This is lecture 15. Let's continue our describing the equivalent characterizations of DVRs. So recall we were trying to prove proposition 38. I'll give the statement again. So we have this integral domain R. With fraction field K. And we had that the following statements are equivalent. The first statement was that R is the valuation ring of a valuation whose value group is isomorphic to Z. The second statement was that R is a Noetherian valuation ring. The third statement is that R is a PID with unique maximal ideal M. And the fourth statement is that there exists an element pi that's not 0 in R, so that every non-zero ideal I equals pi to the m for some m larger than or equal to 0. And we've already shown one implies 2 and 2 implies 3. So now let's show 3 implies, let's continue the proof and show 3 implies 4. So what do we have? We have statement 3 that R is a PID with unique maximal ideal M. And what do we want to show? We want to show statement 4 that there exists an element pi that's not 0 in R such that every non-zero ideal I equals pi to the m for some m larger than or equal to 0. And again, observation, one trivial example of a PID is a field. If R is a field, a field, then the only non-zero ideal is the unit ideal, and then we can just choose pi to be 1. Okay, so suppose without loss of generality that R is not a field. Now since R is a PID, its maximal ideal, it has a unique maximal ideal by hypothesis. So this unique maximal ideal is generated by one element because R is a PID, and suggestively I'll call that pi. Okay, and since we've assumed pi is not 0, we have since we assume that R is not a field, this maximal element is not the 0 ideal, so we have pi is not 0. Okay. So now take an element I in R. Now again, what's the claim? We're claiming that the desired element is in fact the generator of this maximal ideal. So we are claiming that I equals pi to the n for some n larger than or equal to 0. And again, by hypothesis, since R is a PID, what do we have? We have that the ideal I is generated by one element, let's call it A naught. Okay. For some A naught in R. Now, if R is not a proper ideal, if R is the unit ideal, if I is the unit ideal, then I is just generated by 1, and in this case we can simply write I is pi to the 0. So suppose I is not the unit ideal, then I is a proper ideal, and since it's a proper ideal, it must be contained in a maximal ideal, and since R is a unique maximal ideal by hypothesis, it must be contained inside M, that is A naught must be the ideal I is generated by A naught and the ideal M is generated by pi. So we have that the ideal generated by A naught sits inside the ideal generated by pi. And so this allows us to write A naught as a multiple of pi. So let's say A naught is A1 times pi for some A1 in pi in R. Okay, and since A naught is a multiple of A1, what do we have? The ideal generated by A naught sits inside the ideal generated by A1. Now, if A1 is a unit in R, then what do we have? Then the first blue box tells us the ideal generated by A naught is the ideal generated by pi. So we've shown that the ideal I is in fact generated by pi raised to 1. So if A1 is a unit, we are done. So suppose, again without loss of generality, that if A1 is a unit, we are done. So suppose that A1 is not a unit, and again just repeating this procedure. So the ideal generated by A1, since A1 is not a unit, it must be contained inside some maximal ideal. There's a unique maximal ideal, that's M, and that's generated by pi. So again we can write A1 as some multiple of pi. Let's call that multiple A2. So for some A2 in R. And again we have this third blue box, A1 is A2 times pi. So now we have the ideal generated by A naught, that is inside the ideal generated by A1. Now looking at this blue box, A1 is A2 times pi, tells us that the ideal generated by A1 sits inside the ideal generated by A2. Okay, and again now suppose A2 is a unit in R. Well, what does that mean? So A naught is A1 times pi, but what's A1? A1 is A2 times pi, and now we have this other factor of pi. So what we have is that A naught is A2 times pi square, and if A2 is a unit, well, the ideal generated by A naught is equal to the ideal generated by pi square, but the ideal generated by A naught is just the ideal I. And so in this case we win, in this case we are done, since the ideal I is now generated by the second power of pi. So again, just continuing again once more. So suppose A2 is not a unit, do the same thing. The ideal generated by A2 must be contained inside a maximal ideal. There's a unique maximal ideal in R by hypothesis, which is generated by pi. And again you write A2 is A3 times pi for some A3 in R. And again what we have is the ideal generated by A2 sits inside the ideal generated by A3. And continuing from earlier, we have A naught sits inside A1, sits inside the ideal generated by A2, sits inside the ideal generated by A3. And again we have that A naught is A1 times pi, which is A2 times pi, which is A3 times pi times pi times pi, which is A3 times pi cube. So we have A naught is A3 times pi cube. So iteratively, so if we just proceed iteratively, I don't know when I'll stop, but we've constructed a sequence A naught, A1, let's say all the way up to AN, with the property that if you look at the ideal generated by A naught, it sits inside the ideal generated by A1, sits inside the ideal generated by A2, so on and so forth, sits inside the ideal generated by AN minus 1, sits inside the ideal generated by AN. And at each step we have AI minus 1 equals AI times pi. And so if we just proceed iteratively, we have that A naught is AI times pi to the I. Okay, so the question is, can this sequence ever stop? The question is, can AN be a unit in R? Again, if AN is a unit in R for some n, then what does it mean? If you look at this third blue box in this page, we have that the ideal generated by A naught, well, if AN is a unit, it's the same as the ideal generated by pi to the n. And in this case we are done. Since then we would have shown that the ideal I is generated by this nth power of I, nth power of pi. So suppose, for the sake of contradiction, that AN is not a unit in R for all natural numbers. And so we have, so the sequence continues indefinitely. So we have A naught the ideal generated by A naught sits inside the ideal generated by A1, sits inside the ideal generated by A2, sits inside the ideal generated by A3, and so on and so forth, sits inside the ideal generated by AN, and this sequence never stops. So we have this infinite sequence, this infinite chain of ideals. But since R is Noetherian, this infinite sequence must stabilize. This chain of ideals must stabilize somewhere, say at some point R. So we have AR is AR plus 1 equals AR plus 2, so on and so forth. Okay. So what does that mean? So on the one hand, if we have that the ideal generated by AR and the ideal generated by AR plus 1 are the same, we have that AR plus 1 equals x times AR for some x in R. But just by construction of the sequence, we also have AR is AR plus 1 times pi. So combining the above two equations, we have that AR is AR plus 1 times pi, but AR plus 1 is x times AR. And so if we just factor out the AR, we have AR minus x times pi times AR equals 0. So if you factor the AR, you get AR times 1 minus x pi equals 0. But if AR is 0, then you see that A naught, which was AR times pi to the R, would also be equal to 0. But this contradicts the assumption that the ideal I, which is generated by A naught, is non-zero. And so thus AR is not 0. So if you look at this equality, that AR times 1 minus x times pi equals 0, since R is a domain, we must have 1 minus x pi equals 0. Okay, but this means that pi, so this means that 1 equals x times pi for some x in R. But now you have an element x in R, which when you multiply with pi gives you 1, and so thus pi is a unit in R, but this contradicts the assumption that pi generates the maximal ideal. So the sequence that we produce could not continue indefinitely. And what does that mean? There exists an n naught. It says that a n naught is a unit in R. And so again we have that A naught is A n naught times pi to the n naught, with the scalar multiple A n naught being a unit in R. And so this means that I, which is the ideal generated by A naught, is the same as the ideal generated by pi raised to n naught. And so this proves statement 4. And so we've shown the implication that statement 3 implies statement 4. Okay. Now what's remaining? So now what's remaining is we have to show that statement 4 implies statement 1. And so again, what's statement 4? Is that there exists an element pi which is not 0 in R, such that every non-zero ideal I equals pi raised to m for some m larger than or equal to 0. And what do we want to show? We want to show statement 1 that R is the valuation ring of a valuation on K star with value group isomorphic to Z. Okay, so what's the proof? We have to first show that R is a valuation ring, and then we'll come to the hypothesis or the assertion on the value group. So to show that it's a valuation ring, it's enough to show it's a V ring. So by theorem 35 in lecture 13, to show that R is a valuation ring, it's enough to show that R is a V ring. That is, if I give you any element alpha that's not 0 in K, we have alpha belongs to R or alpha inverse belongs to R. Okay. So a small claim before that: every non-zero element alpha in K cross is of the form some unit times pi raised to n for some unit u in R, and n being an integer. Okay. So maybe let's call this claim claim A. Now the fraction field of R is K, so you write this element alpha as R1 over R2, where the numerator and denominator both belong to R. We can do this since K is the fraction field of R. And now again, since the numerator and denominator R1 and R2 belong to R, by hypothesis we have that the ideal generated by R1 is pi raised to m1, and the ideal generated by R2 is generated by some power of pi, let's call it pi raised to m2, for some m1 and m2 being larger than or equal to 0. And so again, what does the first statement mean? R1 and pi raised to m1 generate the same ideal, so R1 is some unit times pi raised to m1, and R2 is some unit times pi raised to m2. Some units u1 and u2 in R. And again, the reasoning is that since principal generators of the same ideal differ by unit. Okay, and so now just collecting all the information that we have that alpha is R1 over R2, but R1 is U1 times pi raised to M1, and R2 is U2 times pi raised to M2. And so what we have is U1 times U2 inverse times pi raised to M1 minus M2. And this proves the claim. Since, well, U2 is a unit, so its inverse is also a unit, and the product of two units is a unit, so U1 times U2 inverse is a unit in R, and M1 minus M2, you're just subtracting two natural numbers, so this is in Z. Okay, so this proves the claim, and now to show that R is a V ring, the observation is just that if M1 is larger than or equal to M2, then this alpha belongs to R, and if M1 is less than M2, then what's 1 over alpha? If you use this formula, it's U2 times U1 inverse times pi raised to M2 minus M1, but now M2 minus M1 is non-negative, so this belongs to R. So if M1 is larger than or equal to M2, then alpha belongs to R, and if M1 is less than M2, then 1 over alpha belongs to R. So this shows that R is a V ring, and what do we have to show next? We need to show that R is the valuation ring of a valuation on K cross whose value group is isomorphic to Z. And for this, what we do is we use the construction of valuations on V rings from lecture 10. And specifically, these constructions are from proposition 30 and 31. So if you had a V ring, so there exists evaluation which is just given by the natural projection map K cross mod R cross and because it's a natural projection map, it's surjective, and so the value group is just K cross mod R cross with the abelian group structure given by induced by multiplication on K cross. And what was the total ordering given on K cross mod R cross? So if you remember, we said that if you take x and y in K cross mod R cross, we say that x over y, x is larger than or equal to y if, well, you pick a lift x and y of the square bracket x and square brackets y respectively, and the ratio belongs to R. Okay, so to complete the proof, it's enough to actually show that this value group, that Z with its plus and greater than equal to, is isomorphic to K cross mod R cross with multiplication and the ordering given above. Okay, so this is not too hard to check, so I'll just write down what the map is. So the map, the group map from Z to K cross mod R cross is just, you take an element n and you send it to pi raised to n. Okay, and again, Y is F a group homomorphism. Again, if you have f of n1 plus n2, that just goes to pi raised to n1 plus n2, the class of that. But just by how multiplication and exponents work, this is pi raised to n1 times pi raised to n2, and so this is f of n1 times f of n2, and that's how the group operation works on K cross mod n cross. Okay, so this shows that if it's a group homomorphism, so Y is F injective. Well, what if f of n1 is the identity element in K cross mod R cross? That is, you have that pi raised to n1, let's say, is the identity element in K cross mod R cross. Again, just unwinding what it means, that is pi raised to n1 belongs to R cross, but pi generates a maximal ideal, so this is only possible if n1 is 0. Okay, so this shows that f is injective. Now, why is f surjective? So take any alpha in K cross mod R cross. What does claim A show? It shows that if you take any left alpha, this is of the form u raised to pi raised to n for some unit u in R and some n in Z. And so now, again, what does this mean? This means that the class of alpha and the class of pi to the n, they're equal to each other in K cross mod R cross, and thus f of n, which is the class of pi raised to n, is nothing but the class of alpha, and so this shows that f is surjective. And the last thing we need to show is why is f compatible with respect to the odd rings on Z and K cross mod R cross. Now again, suppose you have that n1 is larger than or equal to n2. Again, what does that mean? That just means that n1 minus n2 is non-negative. Okay, and now what we want to show that f is compatible, we need to show that f of n1 is larger than or equal to f of n2. But what's the left hand side? This is pi raised to n1, and the right hand side is pi raised to n2. And since n1 minus n2 is larger than or equal to 0, this implies that pi raised to n1 minus n2, this belongs to R, because the exponent is non-negative. This means that pi raised to n1 over pi raised to n2, this belongs to R, but by the definition of the total order on k cross mod R cross, what this means is that pi raised to n1 square brackets is larger than or equal to pi raised to n2 in square brackets. That is, f of n1 is larger than or equal to f of n2. And so this shows that f is compatible with respect to the total orderings on Z and k cross mod R cross. And so we've completed the proof of the implication that 4 implies 1, and this completes the proof of the proposition. Okay, so we completed the proof of the proposition, giving us 4 different characterizations of discrete valuation rings. Thank you.